All right, here we go. As promised, a lecture for Wednesday, September 15th is what it is. So, uh, as I mentioned to class, I am outside of Wisdom, Montana, constructing a bridge. I'm not actually doing the constructing, but I am doing the concrete that's piecing together this accelerated bridge construction project. And so we kind of developed some concrete at MSU that they're using to kind of piece this whole thing together. And so this is kind of the culmination of a bunch of like 5 or 6 years of research of ours. So far, everything's good. They placed all of the concrete in the pile caps this morning, and we're just waiting for that to come to strength, and then we're gonna place the beams, and then we're gonna glue the beams together with our concrete tomorrow. They're probably around 3 or 4 a.m. Tomorrow morning. So, anyways, it's very strange. If you think this is weird to like watch a lecture like this, I am sitting in my camper in the mountains, just talking to myself. So, I'm gonna drive into town later where I get cell coverage, and I'll post this. So, anyways, that's what's going on. Super smoky here. I don't know what's like there. It's a huge fire here. Anyways, let's get started. So we're right in the middle of solving kinetics problem, relating forces to motion, right? That's the whole point of this class. Is as engineers, we design things, and we need to know what kind of forces our objects will feel while they're moving. And conversely, given some forces, we know how things are going to accelerate or move with that with those forces. So, in this class, we're going to cover 3 different methods: FMA, force mass acceleration, where we just use Newton's second law, this equation right here, and we're going to do work energy. That's actually my favorite. And to me, it's the most intuitive. And then impulse for momentum for when there is collisions. So we kind of covered, in this, we're going to cover 3 different coordinate systems: Cartesian, normal, tangent, and polar. We have thus far covered Cartesian. We're going to do normal, tangent today. And then when I see you guys on Friday, we'll do polar, right? And then we'll move on to work energy and do the same thing, and then on to impulse momentum, and kind of finish things up and take an exam. So the exam's going to be in 2 to 3 weeks, 3 weeks maybe. So just keep that on the radar. So in Cartesian coordinates, just kind of broke this governing equation into its x, y, and z components, and then we just came up with 3 equations of motion. So we get 3 equations of motion to use, and we added in this idea of or I guess a solution procedure. We're going to draw a free body diagram, write down the equations of motion, kinematics as required, and solve. And so this will stand for all the different coordinate systems, not just Cartesian coordinate system. And then I gave you a little checklist for making a free body diagram. Okay, and we did an example of kind of a spring, mass hanging from a spring. And then we did another example of a ramp where we pulled on this string and this thing, or on this cable, and that this thing would move up or it would move down depending on how much we pulled on it, and we kind of controlled that acceleration. So that was the problem we finished up on Monday. So today, let's do a new coordinate system. In this case, the coordinate system is the normal tangent coordinate system, right? And super quick derivation of this, and we'll do a couple of examples. So to kind of start things off, we'll just kind of refresh your memory on what the normal tangent coordinate system is all about, and what we include in it, or how it works. Page of notes here. So normal tangent coordinate, just a refresher. We've got an object that's this particle is moving along a path. Moving along this path, right? The particle's moving along that path. And so we have to write down what that coordinate system is. Right? If you have a path defined, sometimes it's easiest to use this normal tangent coordinate system as opposed to Cartesian coordinates. And so we have one coordinate that's going to be normal to that path, tangent to that path, and then another coordinate that's going to be normal to the path, pointed towards the instantaneous center of curvature. So in this thing right here, this would be ET hat, and this is EN hat. Okay. A component that's traveling tangent to the path, and a component that's normal to the path. Okay. In terms of velocity, all of the velocity is always in the ET direction. And so that is what this is right here. All of the velocity is in the ET direction. There is no normal component to it. It's kind of part of the definition of this coordinate system kind of states that, right? We have a tangent. Velocity is always tangent to the path. If it's not, then it's not on the path. Okay. The acceleration is defined as such. We have a tangent component, AT in the ET direction, and AN in the EN direction. The AT component is how the speed is changing. That's what this is. How is the speed changing? That's kind of like if you're in a car stepping on the accelerator, it's how you're accelerating along the path. Okay. Then the other component has to do with change in direction. That's this here. And there's kind of a couple different forms to it. Right? I wanted to box that. A couple different forms to it. Right? We could either use rho omega squared, or we could use v squared over rho. And just kind of depends on whether or not you know omega. Sometimes you do it on a problem and you know omega. Sometimes you do it on a problem and you know velocity, right? And depending on which one it is, you use either this guy right here or use this guy right here for those for that acceleration component normal to the path, which is the acceleration associated with change in direction, right? Sometimes you hear of this is called centripetal acceleration, right? It's how, right, if it's right, velocity is a vector, and so I'm traveling along a path. I need to change direction, not just speed, but if I'm changing direction, I am changing my velocity. If I change my velocity, that means I'm accelerating, right? And this is associated. So this is the acceleration associated with that change in direction. It's either v squared over rho or rho omega squared. So that's kind of the kinematics that we've kind of covered thus far, right? So we come down to our equations of motion. Right? Here they are right here. Some of the forces, right? We have, so you the same. We start out with the same vector form, right? Sum of the forces external is equal to mass times acceleration. Right? So we start out with that same equation. It's just now acceleration is in the, we have these components of the acceleration. We have in the tangential direction, it's equal to this, and in the normal direction, it's equal to this. So we look down at our equations of motion. We have two of them for this coordinate system. You could also add a z component to this and turn this into a 3D problem, just kind of like what we did in polar coordinates. But right now, we'll just treat it as a planar motion problem. So we have this equation of motion. Okay. So sum of the forces in the t direction is mass times acceleration in the t direction, which is just mass times v dot. Right? How is that speed changing? Right? And then we also have in the normal direction, sum of the forces in the normal direction is equal to mass times acceleration in the normal direction. And we either use mv squared over rho or m rho omega squared, depending on if I know omega or whether or not I know v. And so these components right here, that's just this v squared over rho comes from that right there, or rho omega squared comes from this. And so it just comes from our definition of those accelerations in those two different directions. So what I do is I draw a free body diagram. I look at all my forces in the t direction, and I set that equal to mv dot. I look at all my forces in the n direction, and I set that equal to mr omega squared, or mv squared over rho. Okay? Either one. Simple as that, right? It's as simple as it sounds. So that is it for the derivation of normal tangent coordinate systems and kinetics, FMA. Okay, so let's do a couple of examples. So I picked this because General Lee is known for jumping. Okay? I watched this show a lot as a kid. There's the Confederate flag on top of this, right? I don't think that this. Anyways, it's very political. I chose this before. This was political and whatnot. So this is the General Lee kind of coming over the crest of this hill. Okay, so that's shown. So the crest of the hill has a radius of 200 feet. So this car, General Lee is traveling around the crest of this hill, is traveling like this. right? And you can imagine if they go very fast, they jump, right? If they go slow, they stay on the surface of this. And so what this is asking is, what is the maximum speed that the car can travel without leaving the surface? Or you could think of it as, what is the minimum speed required for this thing to leave the surface? So either one, it's the same value. Okay, so it has a radius of 200 feet, and then it's traveling around this. So this is, it can be solved as a normal tangent problem. It could also be solved with polar coordinates, because it is a circular kind of motion that this thing is traveling around. But regardless, we're going to do this thing in normal tangent coordinate system right now. Okay, so the way we start all of these problems is we start out with a free body diagram. Right, this should just be the standard. Right, all of these kinetics problems start out with a free body diagram. Right, even the work energy problems that we're going to get into, we're going to draw free body diagrams for them. So draw a free body diagram. We isolate the mass. Right, so I'm going to isolate my mass. Okay. And then I'm going to look at all the reactions at play and all the forces at play. So kind of my forces here, we have a normal, well, I would say I like to start with gravity. We do have mass times gravity acting down. Where's my straight line? Okay, I got mass times gravity doing that. I also have a normal force acting up. Okay. And that is it for forces. Okay. Could I have a force, kind of like a thrust on the back of the General Lee? Yes, I could. I could do that if I was accelerating. If the General Lee was accelerating, right, there would be a force, like a kind of a torque force, right? The tires would be cranking away, which would be accelerating the force. But I believe it says it's traveling at a constant speed right here. It's traveling at a constant speed. So there is no kind of thrusting force behind the General Lee at this point. So the only thing I have is the normal force and mass times gravity acting down. Okay, I'm not done with my my deal here, my free body diagram, because I need to put in the coordinates, right? We said this is going to be a normal tangent coordinate, and it is, right? And so picture this guy's traveling along this path right here. We can have a tangent right here and a normal right here, right? A tangent to the path and normal to the path, right? And so what that coordinates are going to look like down here, that right there is going to be my ET hat. And this guy right here is going to be my EN hat. Right? Tangent to the path and normal to the path. So that is my free body diagram. Okay, of all the forces that are there and my coordinate system label. There's no real angles or anything like that to define at this point. So that's it. That's my free body diagram. Okay, second part of the problem solving strategy is to write my equations of motion. AOMs. Equations of motion. Okay. And so I have two different directions to deal with here. I have the t direction. Right. The t direction. In the t direction, I'm going to sum all my forces. Sum of the forces in the t direction is equal to, in this case, 0. If we look up at our free body diagram, there are no forces in that direction right there. So my sum of my forces in the t direction, which tells us that our MAT, and there is no acceleration in that component, so that's just mv dot, which is equal to 0. So there's nothing happening there. My forces are 0, therefore my accelerations are 0, right? The problem statement says the accelerations are 0, so the forces are 0. So there's all sorts of reasons why that's 0. Okay, so the t direction, a little more interesting stuff happening in the n direction. Right? In the n direction, I say, some of the forces in the n direction, we look at all the forces in the n direction. We've got n going up, which is in the negative en direction. So this is a minus n, right? So you can look here, right? En is going this direction, n is going this direction, so it's the negative n direction. But then mass times gravity is acting in the positive direction, so that's going to be a positive mass times gravity. And that's equal to mass times an. And so it's asking for the minimum speed, which is a velocity, right? So I'm going to use the mv squared over rho version of the an acceleration, right? So this is equal to mass times an. I could choose mv squared over rho, or I could do m rho omega squared. The problem statement asks for the minimum speed or the maximum speed, and so I'm going to just go straight to velocity here. I could solve for omega and then take that omega and kind of back solve for I could take that omega and then multiply it by rho, and then it would give me the velocity, or I could just go straight in and solve for the velocity using this version of the acceleration. Okay? Almost there, except I've got a bit of a problem here, right? I know mass times gravity, right? It tells me that my 3,500 pounds, so I know mass times gravity. I know rho, but I do not know velocity, and I do not know the normal force, right? And so I have too many unknowns. I have one equation and too many unknowns. So I got to think about the problem a little bit, okay? I'm trying to find the minimum speed so that this thing jumps, okay? What will happen when this thing jumps, right? If this thing takes off, what happens to the normal force when that thing takes off, right? When that thing leaps, that guy goes to zero. Right? There will be no normal force when this thing jumps. Okay? Hopefully that makes sense to everybody. Once it leaves the ground, and so we're trying to find the cusp right when this thing launches. If I want to find right when this sucker launches, right? It's going to be right when that normal force just goes to zero. Right before it launches, it's going to be a value. Right after it launches, there's especially in the general Lee, it cannot be held down to this thing right here. And so right at the cusp of the thing jumping is going to be when that normal force is equal to zero. So in this case, this problem right here, that sucker goes to zero, right? And so that eliminates one of the unknowns. The other thing that kind of going to cancels out here is the mass, right? The mass ends up being on both sides of the equation. And so those two cancel each other out. So it's kind of interesting that the solution is going to be independent of how much the thing weighs, right? What the mass of the object is that goes by, or as it launches here. And so really what you're left with is this. G is equal to v squared over, kind of an interesting finding that the mass doesn't play into this solution in any way. Okay. And so we know what G is, right? 32.2. I know what rho is, which is 200. Is equal to v squared over 200. And so if you solve for that velocity, I just plug that sucker in my calculator, is 80.2 feet per second. Right. That is what my answer is. Okay. And then, like I said, nothing going on in that t direction. Everything was happening in the n direction. And then we had to kind of think about it a little bit and know that that normal force goes to zero. Cool beans? Cool beans. Okay. One more problem here. More going on with this thing right here. Okay. So we have, and I'll show you a video of this. This is leading up to my YouTube Friday. Sorry, I'm going to grab a drink really quick. YouTube Friday. So on Friday, I'll show you a video, kind of what this is about. So what this is 1,000 pounds of people. Okay, so multiple people are standing right here, and they jump off this bridge. They're tied to it. They got a rope attached to them, and they go whoosh, and they swing. The big giant swing, and they have a radius of 200 feet. Both of the problems, yeah, they both have radii of 200 feet. So they jump off, kind of go around there. Okay, if the rope has a capacity of 1,500 pounds, or I guess 2,999, I modified it. It has the capacity of 2,999 pounds. Will everybody be okay when they jump off of this? Okay. Drink here. Okay. Alrighty. So, how do we solve this problem? Great. Stick to our method here. Our method is we start out with a free body diagram. Every time. B, D. Okay. Not a lot in this free body diagram, but enough to help us out here. We have isolated mass. That's 1,000 pound of people. My favorite thing to write every time is going to be, we have mass times gravity acting down. Mass times gravity. And then I'm going to write this. I'm going to draw the free body diagram at some random location. We're going to draw it like here, right? Where that tension force is going to be. It's going to be dependent on where they're at in the swing. We're going to write this as a function of theta. So I have a tension force acting up and to the right. And like I said, I'm going to do this as a function of theta. So again, so there's all our forces. I think that's everything. There is no drag. We're going to ignore the wind and stuff like that acting on it. So this is all we got. And then we're going to do this as a function of theta, because that theta is going to change as it swings down, right? I'm going to start out at 0 and then work its way up and go from there. Okay, so there's our free body diagram. We have not labeled yet our coordinate system. In this case, our coordinate system is, we have the normal to the path is going to be this way. I'm getting right along that tension. That tension force is going to act normal to the path. There we go. This is going to be En hat. And then tangent to the path is going to be right. Oh, I'll put it over here a little bit. This is Et hat. On this drawing over here, we could see it, right? Tangent to the path and normal to the path is what our coordinate is. So on our free body diagram, it looks like that. It's not quite right. Those should be normal to each other. There should be a right angle between those two, between the normal and tangent to the path. I'm going to leave it right there, though. I think you can see mainly what's happening there. Oh, I can't do it. I'm an engineer. I can't do it. I'm going to correct that. Tangent's going to be more. That's a little better. I'm trying to leave some room here. I'm going to go over here. Better. That's ET. It should be 90 degrees to that. Okay. The reason I wanted to leave a little bit of room is because this mass times gravity term is going to get broken into two components. Just kind of, sometimes on my free body diagram, I like to kind of show what the components are. There. Right. The mass times gravity has to get broken into its normal component and its tangent component. And so sometimes I like to do that and label all the key angles. That'll be an angle theta right there. Right? It's going to be theta, not theta, theta. Okay, and so mass times gravity, we're going to have a component that way and a component this way. Right? I think that's everything. There's my free body diagram. I got my coordinates labeled. I got my angles labeled. I got all my forces labeled. Right? I even broke it down, my forces, into the different components. We're good to go. Okay. So next in our solution process is to write the equations of motion. EOM. MS. Okay. We have two equations of motion. Some of the forces in the some of the forces in the normal direction and in the t direction. So let's do the normal direction first. And direction. Some of the forces in the n direction is equal to, look at all, so at this point, just look at your free body diagram and say, what's all going in the n direction? Well, t is going in the positive n direction, and then mg sine theta is going in the negative n direction. right? So this is going positive direction. This part is going into the negative direction. So then that's what we write down here. We write this is T minus mg sine theta. That's equal to MAN, which we will do that's either equal to mv squared over rho or mr omega squared, either form. Okay, that's that, right? You draw a free body diagram. You write this force is equal to mass times acceleration. You expand the forces by looking at my free body diagram, and I set that equal to, whatever version of mass times acceleration, or whichever form of acceleration we want to use there, times the mass. Okay, in this case, I'm going to use this mr omega squared. We'll see that in a second. Okay, but not enough to solve the problem at this point, right? I can't solve it yet. I just know I've just written down that equation. So now I got to look in my t direction. All right. So now we just sum of the forces in the t direction. Now we look at our free body diagram. Say what's all acting in the t direction. Well, I've got that component of mass times gravity. That's it. That component of the weight. Right? And so that is mg cosine theta, and that is in the ET direction. So it's in the positive, right? That's acting like that, which is in the positive ET direction. So this is just mg cosine theta is equal to MAT, which is equal to mr alpha. So if you look at a circle, this thing is traveling in a circle. So if you look at your kinematics for an object traveling in a circle, and you look at normal tangent coordinates, that simplifies down to this. MAT, the AT simplifies down to r times alpha. All right. You look back at your circle notes for the kinematics of normal tangent coordinates, you'll see that. So again, what's interesting is your mass kind of cancels out here. Okay. And so we could kind of rearrange this and get alpha. Right? We need our acceleration equation. So this is alpha is equal to g times cosine theta divided by r. I should mention that, like, these types of problems where you talk about, oh, what's the velocity up at the top, and I'm trying to find the velocity down at the bottom, right? And I mean, just to kind of give you a heads up here, once I know the velocity down at the bottom, right, v squared, once I know what the velocity is at this point right here, I put in that v, boop, I know all this stuff, I can solve for my t. What I'm after is t here. Once I solve for this t, then I can compare that to the 2,999 and see if it's going to be okay. If that t is bigger than 2,999, things are going to be a problem. There's going to be a problem. If that t is less than that, everything's going to be okay, right? The max force is going to happen when this thing is down at the bottom, when it's traveling the fastest, right? You can imagine this thing jumps off. They're going to be going the fastest right here. If they're okay down at the bottom when they're going the fastest, everything's going to be okay. Once I know that velocity, I take that velocity, plug it in right here. Then that will tell me what my t is. Once I know what that t is, I compare that to the allowable and see if I'm going to be okay or not. Okay. So kind of we got that kind of figured out. So I need to figure out what the velocity is down here at the bottom. Right now, I have the acceleration as a function of position, right? It's alpha, but it is still an acceleration. I have alpha as a function of position, right? And so this is where kinematics comes in. I did my free body diagram. I did my equations of motion. I kind of set up the problem. I have one equation of motion. I have another equation of motion. I'm kind of stuck because now I have acceleration as a function of position, and I got to keep going to figure out what the velocity is down at the bottom, right? And so at this point, you would look back. Again, this is accel function of position. Oh, the point I was trying to make a second ago when I went on the little tangent thing was, what comes up a lot is like, oh, here are these people up at the top that I want to know what the velocity is down at the bottom, and go, These problems scream work energy. If you could use work energy right now, if we knew how to do it, we don't know how to do it yet. But once we do know how to do it, this problem cake with work energy, right? The velocity up at the top, I know what the potential energy is. I know what the kinetic energy is up at the top. All of that potential energy goes into kinetic energy down here at the bottom. All right. So it's mgh is equal to 1/2 1/2 mv squared. So mgh is equal to 1/2 mv squared. I solve for that velocity. I take that velocity, I put it into here. Boom, done. We don't know how to do that yet, so we have to do this kind of a little bit longer approach to get there, which is going through this acceleration equation. Okay, just wanted to point that out. So there's my acceleration function of position. If you look back in your notes, we talk about how to solve acceleration as functions of position. Okay, right? It's alpha as a function of theta in this case, but which is an angular acceleration, a function of angular position, which is theta. So alpha is equal to, if you look back in your notes, this is how you solve these problems. You got to use the chain rule, d omega dt. Say d omega d theta, you multiply by d theta over d theta. Right? This is just omega. And so this is d omega d theta times omega. Right? Put all your omegas together and all your theta stuff together. So you take that d theta and put it on the other side. So this is alpha d theta is equal to omega d omega. Okay. I can expand. I know what alpha is. Alpha is g times cosine theta. And that's what we just solved from this equation, from our equation of motion above. G cosine theta divided by r is what alpha is, d theta. I'm going to integrate this side of the equation. I'm going to integrate this side, omega d omega. This guy is going from 0 to pi over 2. Why pi over 2? Pi over 2 is the angle of theta when it's down at the bottom. It's the angle when these guys are in this position down here, right? That theta is pi over 2. All right, so I'm going to integrate this from 0 to pi over 2. And then on this side, I'm going from 0 to omega. I'm after that omega that's up here. I'm after that omega right here. And so I just plug this thing into my trusty TI-89, and it tells me that omega is equal to 0.567 rads per second. Okay, so that's not my velocity, but that is my angular velocity. Okay, and I could take that and plug it in to this version of the equation above here. Right, this is going. Right, I'm going to use that form because I just solved for omega instead of velocity at the bottom. I solved for omega at the bottom. And so since I have that omega, I'm going to use this version of my acceleration. So I take that, plug it into the equation above. The only unknown is t. So let's do that. So this becomes t minus mg sine theta is equal to mr omega squared. I could solve for t. T is equal to mr omega squared plus mg sine theta. I'll plug in all our values. I'll go ahead and put them in so you can see them. T is equal to, the mass is, you be careful of your mass, right? It's 1,000 pounds of people. It's pounds, so I have to divide by G, so it's that was the weight. 1,000 pounds is the weight, so I have to divide by 32.2 to give me the mass. So it's 1,000 divided by 32.2 times the radius is 200. Right, that's the radius, times omega squared, which is 0.567, which we just found. That value squared plus mass times gravity, which would be 1,000 in this case. You could do 1,000 divided by 32.2 times 32.2, which would give you 1,000, but we could just put in 1,000 there, times sine of pi over 2. Right? And if you solve this, carry out that math right there, you get a tension value of, would you look at that, 3,000 pounds. Okay. Boop. Okay, 3,000 pounds. So is there going to be a problem? Yes. Yes, there's going to be a problem. The capacity of the rope is 2,999. They will hit a maximum tensile force in that rope of 3,000 pounds. The rope is going to break. Okay. What would happen when the rope broke? Rope breaks. They're going to come around like this. And then right here at the bottom, right when it hits, it goes from 2,999, right? So right before the end, it would be 2,999. Boom, snaps, right? And so they're going to go, boo, okay? They're going to shoot off to the side, right? They're going to go flying off on a tangent. The reason they're going to go flying off on a tangent is there is no force acting back toward, there's no normal force acting back towards the center of curvature. If there's no force that direction, there's no acceleration that direction. If there's no acceleration that direction, they go straight. There is no change in direction because there is no normal force because the rope is broken, okay? And so we'll watch a video of this on Friday. Nobody dies. Everybody's good. Some injuries, not too bad, but we'll show some folks jumping off a bridge. And then, so next topic that we'll cover, we'll save this until Friday's lecture, but we're going to do polar and cylindrical coordinates. Okay. Very quick derivation of these things. You kind of get the hang of it, I think. We'll do an example problem and maybe 2 example problems actually, and then talk about some other interesting things that come from polar cylindrical coordinates, and then work our way into work energy. Orbital motion, that's the thing that's kind of neat to see. Polar coordinates with FMA kind of explains orbital motion, which is pretty neat. All right. I will see you guys all on Friday. I have no idea how long I've been talking here. I might need to give a little bit more. Just thinking, I forgot about orbital motion. Hold on. Let's just do that while we're here. Let's do this. Okay, it'd be really quick. Hang with me. So, hang with me for a few more minutes here. Okay, I just want to make sure we have enough time to do some examples on Friday and then get into orbital motion and stuff like that. Okay, so the last coordinate system we're going to do with FMA is polar coordinates. Like I said, you're getting the hang of this. Okay, getting the hang of this. In this coordinate system, right? Just to kind of refresh your memory again, we've got the origin, we've got a vector pointed to the particle. We have one of our coordinate directions is just continuing along. So this is R bar. It's continuing in the R direction. So that's ER direction. And then perpendicular to that, normal to that, we have the E theta direction. Okay. Maybe I can angle theta down here. So that's that coordinate system, right? It's different than a normal tangent. Sometimes they line up in a circle, they line up, but typically they would not. Okay. And so just continuation in that direction, continuation in the radial direction, and then you have the E theta for increasing theta direction. Okay. The velocity, right, is R dot in the ER. How's the R getting bigger, and then R omega in the E theta direction. So that because of the omega, there is a velocity associated with that. And then if R gets bigger, there's a velocity associated with that. The acceleration is what we're going to be using in these types of problems, right? The acceleration is, here's the components in the ER direction, and here are the components in the E theta direction. This is pretty complicated. There's a lot going on. Right, this is the radial acceleration. This is the centripetal acceleration. This is tangential acceleration or transverse direction, and this is Coriolis. So they all, we talked about and showed you like I used the analogy of walking around on a merry-go-round, right? And all of these accelerations kind of have a reason and a purpose, okay? And then we add it to turn it into cylindrical coordinates. We just add in z acceleration in the k direction or z velocity in the k direction. Okay, so that's that coordinate system. So we come down to our equations of motion. Here they are, very straightforward. Sum of the forces in the r direction is equal to MAR. What's AR? Well, it's AR from up here, right? It's just the R double dot minus R omega squared. So when we write when we solve these types of problems, we write the equation of motion is mass times acceleration in the radial direction, and then we write this whole thing for the AR component over on the right, and then we write all of the forces that come from our free body diagram in the theta direction. Okay, same idea. We sum up all of our forces in the theta direction. So we look at our free body diagram, we find all those, we expand this into all of its components, and it's equal to mass times the total A theta, right? Some of these terms may go to zero, but you write the whole thing, right? And that's another equation that we get to use to solve these problems, okay? And then the z direction, same deal. If it's a 3D problem, we're going to do some 3D problems when we meet next. So you sum up all the forces in the z direction. It's equal to mass of acceleration in the z direction, which is just mz double dot, okay? Now we'll stop. Now we've covered that. So then next time we'll do this problem, which is a 3D problem. We'll do this very similar 3D type problem, and then we'll start talking about orbital motion. But you can see that, right, this problem in particular, we're whipping this thing around. It's a ball and a string, and we're whipping it around. How fast does it need to go in order for this ball to kind of stay stationary in the air, right? If you imagine if you stopped moving, it would fall. If you moved it as fast as you could, it would be like more horizontal. So how fast does it need to be to hold it at that angle, 85? So you can see that's a 3D type problem. Anyways, officially, that's it. Okay. And I will see you guys on Wednesday. Break.